Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. This is the second of 3 videos that I am going to show you from my student presentations in the deep learning class. The major project that these students work on in the class is a Kaggle competition. In this competition, what they were tasked to do was count the paper clips in an image. Now, this is very applicable to the real world. They could be counting cars or houses or something from a satellite image or other things. This semester for Washington University, like many universities, well, pretty much every university, has been online. So these presentations that the students gave were done through Zoom. And this gave a great opportunity to put some of these onto the internet on YouTube. The students were kind enough to give me permission to post their videos, and I selected from the ones that covered a decent number of technologies that I wanted to show you. The one that I'm showing you today makes particularly use of ensembling and also talks about how the students were able to combat some of the load on the internet. So Google Colab seemed to be very slow during the part of the COVID-19 outbreak that they were trying to get the compute resources. So they used some creative techniques to do this. Let me introduce the team. This is team IDKY. The speaker is Jifan Zhang, and the team members are Cheng, Zhao, Zhanwen Liu, and Ruohan Zhao. These are all graduate students in analytics-related majors. So without further ado, here is Zhifan.
Hi guys, I'm team. I'm sorry, I'm from team IDKY Kalbeer. Okay, and my team member is Yang Cheng, Zhanwen Lu, Zhao, Ruohan Zhao, and I'm the speaker, Jifan Zhang. All right, first let's start with a comic, and this is a screenshot from the LinkedIn, and it's really interesting. It says the woman says 1 year on this planet is like 70 years on Earth, and the man says, great, I'll train my deep learning model here. And it's definitely true because whenever you train a deep learning model, it's gonna take a long time. All right, so let's get started. First of all, I'd like to talk about the tools that we used first. So first of all, is our old friend that is Collab, and I've summarized several good points and down points. And first, the Collab is very friendly for developers because it actually provides a very friendly developing environment. For example, when I did the preprocessing step, and I need to deal with every pixel from the picture. So I use a method from the NumPy library. It was called apply along axis. And at that time, maybe you will just like forget what the name of the method is. So in Collab, you can just type NumPy dot apply underscore, and it will just automatically to remind you that there is a method called apply along axis, and that's really friendly, I think. And second, the Collab is very cool about having provide you with a free GPU. For example, is Tesla K80. It's about several $1,000, and that's good. And third is the Collab. It can also provide you with a huge storage. And I remember if you have a free Google account, and you can apply for a 15 gigs of storage. And if you have a student account or like a company account, you can have up to unlimited storage. And one of the good points that you have so much storage is you can store many intermediate models inside your Google Drive, and that's going to be important if you want to do some ensemble methods. And here is some dumb points for Collab. And the first is the I/O performance of Collab is really devastating because the Google Drive and the virtual machine, the connection is very poor. It's like it's just like it has some magic to drive you mad. And whenever you just start a virtual machine and you want to connect to your Google Drive, it will take like 5 minutes before you can actually to successfully mount to your pictures. And the second dumb point is the Collab has some unexpected cutoff. And I have some bad experience about this because I remember one day before I sleep, I just set up the whole model and I clicked run. And hopefully I thought that in the morning I can see the results and everything is perfectly on my screen. But the next day when I woke up and I opened my computer, it says, wow, the Google Drive, the Google Collab has cut you off, and it's not even trained for one complete epoch. That is really bad. And that's the reason why I approached to the second tool that was called the Paperspace. Yeah, and the surface, that's me. And that's the reason why I approached the second platform. It was called Paperspace Gradient. And here's the good points and down points. Good points is it also provides with an excellent free GPU. For example, Quadro P5000 and Quadro M4000. And they were about, I remember it was about $1,000 GPU, I think. And Paperspace also provides you with a fixed time cutoff. Is for a fixed 6-hour runtime. So you can have some plan before the cutoff. For example, if your program has run for 5 hours and next you're gonna like to store your whole model and before Paperspace has cut you off. And the virtual machine has 8 core of CPU and 30 gigs of RAM. And I remember Collab has only 15 or 25. And the IO performance of Paperspace is a lot better than Collab. But the down points is also very it's a little bit severe because it only provides you with 5 gigs of free storage, and of course you can upgrade to some like 200 gigs of storage and so on. And the 6-hour may be just not enough for you to train a deep learning model. So next, let's talk about the pre-processing. And what we've done is actually similar to the previous group, but we have did something different. Oh, I'm sorry. Basically, we are just gonna first of all we're gonna delete the white background and the red lines and the blue lines. And how are we doing this? Here's the code. We've defined a function, and the function will take in every pixel of the picture. First, I'm gonna examine the maximum channel of the pixel. If the maximum value is greater than 210, it means that the pixel is actually a white pixel. So what I'm gonna do is to make the white pixel whiter, because the picture is coded in RGB. So I'm gonna make that pixel into triple 255, and just to directly run the last line of this code. And for the second if condition is if the maximum channel and the minimum channel, the difference is smaller than 10, it actually means that the pixel, the color of the pixel is like gray. So the gray pixel should be a pixel on the real paperclip. So that's the pixel that I'm gonna keep. I'm gonna directly return X. And for the else if condition, if the maximum and the minimum channel is smaller than 80, it means that it's a pixel at the interaction between the blue or red line and the clip. So when we encounter this kind of pixel, I'm gonna put triple the mean of the 3 channels to make it a complete gray pixel. And one thing to note here is whenever you want to fill in a new pixel, you need to specify the data type to be unsigned integer 8-bit, because that is very important, because if you don't do this, you will get some really strange output. Yeah, and in NumPy library, the default is gonna be integer 64-bit. Yeah, and then we did the feature engineering process, and this process takes us to the RMSE of 2.0. And we've chose 3 different features. The first is the size of the picture file. The second is the gray pixel count, and the third is the dark pixel count. And the third I need to explain better, because what is a dark pixel? Because we believe that if there is more clips, there's gonna be more or less darker pixels, for example. And the cutoff for a so-called darker pixel is gonna be the triple 50. Yep. And we've drawn a picture we've drawn a picture on the left of the screen, and the horizontal axis is the true count of clips, and the y-axis, the vertical axis, is gonna be the feature value. And you can see here the second and the third features, the gray pixel count and the dark pixel count, are good indicators of how many clips are in the picture. But the size of the picture file is it performs a little bit worse. And then next, we've asked ourselves a question: is what to do next? And it was actually a very, very hard to answer question, because we've tried a lot of methods, but most of the methods just doesn't work. And first, first we've tried on Collab, and we've tried to write a batch picture generator, and also we've tried to use the flow from data frame the method. But actually sadly the Collab IO says no. We just can't do this because I remember one time that I trained network, and the process is really slow. And at first I thought that Google Colab has cut me off from GPU usage, but actually it was something related to the I/O. And second, we've also tried to swallow the whole data set into RAM. And at first we cannot just normalize the integers into floating points, because the Colab RAM just doesn't allow this. I can remember the size of the training set. It was about 5 gigs, I think. And if you convert to unsigned integer 8-bit to floating point integer, to floating point 32 bits, and it's gonna take 4 times more RAM to swallow the whole data set, and that's gonna run out of the Collab RAM memory. So we just cannot do this. And then we've tried to convert to Boolean. Yeah, this method it actually worked, and we got a RMSE of 0.93. Yeah, what's more, we've also tried. We've also. Oh, there's a question. Let me see. What does convert to Boolean mean? It just simply says if the pixel is not completely black, which means the 3 channels are all 0, then I'm gonna convert that pixel into true. Only one value, true. If the pixel is triple 0, I'm gonna convert that pixel into false. It's just that simple, to basically to save my RAM. And I'm gonna continue. So then we've also tried the VGG19 model, ResNet model with transfer learning. But sadly, what we've seen is the validation loss is like jumping. Sometimes the validation loss is 10, sometimes is 50, and sometimes is 5. It's just like jumping all around. So we just believe that ResNet model may not converge to a smaller MSE in a short time. So we've just given up. And then after I chose Paperspace, and I said, well, why shouldn't we just define a convolutional neural network model without transfer learning? So and then the next page I'm gonna discuss about the model that we built up. And first, and the code shown here is the model that we've developed. One thing to know that is these parameters, like the 64 filters, 128 filters, we have tried different combination of these. For example, we've tried the first convolutional layer. We've tried to use 32 filters, and the second we've tried to use 64 filters. And we found that when we use 64 and 128, it's gonna perform better. And and after that we added a flattened layer and 3 dense layers, and that's basically the structure of our neural network. And after compilation, and we gonna save the whole model into the storage. One thing to know that we've also tried to use the batch normalization process after the convolutional layers and the dense layers, but it also makes the loss so jumpy. So we've just deleted that code, and we've set up our model. Oh, and there's one more thing is about the checkpoint, and Peter has also mentioned this. It's very important, because for Paperspace, it will cut you off 6 hours later. And every time you train a model, it's like it's gonna take you 10 minutes for one epoch. So which means in the 6 hours, if you can fully utilize the 6 hours, it's gonna take you to 36 epochs. But that's not gonna be enough for you to train a deep learning model, because the final model that we've trained, we've trained for about 200 epochs, I think. So simply just 6 hours is far from enough. So we have to create some checkpoints, and then we're gonna feed the model, and then wait. Yep. And this model takes us to the RMSE of 0.73. And after that, I've tried to change different parameters of our CNN network. We've tried this for several days, and finally we've decided to use the previous code that I'm showing you. And until one day, I found that when I was training, I have manually stored 20 model checkpoints to my storage, and the checkpoints are listed on the right of the screen. And the number in the parentheses is the MSE. Actually, it's not the RMSE. Don't get me wrong. And so I was just wondering, what about I can just average these two best model predictions? What will the result be? Will it be even better than simply using one result? And I've tried to average it, and something could happen. And the ensemble model take me to the RMSE of 0.68, which led us to the first place on the public leaderboard, and for one day, and after before beat up by you guys. And then we've tried to see how each of the model have performed in terms of the prediction. They perform really similar, and for the papers that have more clips, the prediction is not so accurate than the pictures with fewer clips. Yeah, and here comes a question: is how should I better ensemble these these models? What we think about is here are several like very state of the art methods that can help us assemble the models. But finally, we've decided to use the linear model to assemble all these models in the orange box. And this leads us to a RMSE of 0.66, which is the fourth place in the leaderboard. And what's next is something that we've gotta think about. And these are some things that we haven't tried, but is worth trying. And first, I think I can give some pictures, such as the pictures with about 75 clips. We should give more weight to these kind of pictures. It will act like a kind of penalty if the model has mispredicted the number of clips in these pictures, and the MSE will be greater than it should be, and that will act like a kind of penalty to the model, and the model will count better for the pictures with more clips. And a second, the original picture is a RGBA picture, and we've made it to RGB. I think maybe in this process, maybe we have lost some information. So next time that if I were to do this competition a second time, maybe I'll consider the alpha channel, take the alpha channel into consideration. And third, I'm gonna try more assembling methods, not only the linear model, but also like random forest, something like extreme boost, something like this. And the fourth, we've got to further optimize our convolutional neural network structure. And basically we've simply used 4 convolutional layers. Maybe in the future, maybe I can use 6 or 8, or maybe I can just simply use transfer learning to use a pre-structured convolutional neural network. Maybe that will perform better if I really have the patience to train more epochs. And the fifth thing that I think of is to assemble after assemble. Because I've only assembled for one time, which is a linear assemble. What about I can assemble for first I can use a linear, and second I can use a random forest, and third I can use an extreme boost. I can reassemble these 3 outputs into one single prediction. Maybe that will act better, but who knows? And that ends my presentation, and thank you guys. Here's the Q&A process. Give me questions. Thank you.
Very good presentation. Thank you very much, Zhifan. Any questions from the class? See, there's one in chat that just popped up from Peter Lee.
I can't find the original paper, but I also have the same issue of jumpy training loss and validation loss at search Google. It seems that batch model training and batch optimization having jumpy loss. Yeah, I agree. the validation loss is just like jumpy. So actually, I don't have that much patience to further train the model. But maybe if I really have the patience, I'm gonna take more time. Maybe the loss is gonna be converged to a smaller value. How does your team obtain the parameter for preprocessing? Oh, that's very interesting. Basically, we've tried a lot of parameters. These you can see the 210 and the 80. We have tried a lot of we've tried a lot of different combinations. For example, 250, for example 200, and sometimes 190. And finally, we found that 210 is a best parameter that can clearly distinguish the background and the clip. Yep. Any more questions? You do that by look or by stats? No, it's simply try. Just trying. Just keep trying until I can see the picture is more distinguished. Yep.
Any other questions from anybody? Very good presentation.
Thank you.
Let me, so I'll make a few comments and maybe, so first, that's great that you used Paperspace. I had heard of that, but I was not familiar with that. So that is definitely on my list of things to check out. Mm-hmm. So probably in the Kaggles in the future semesters, I'll put a list of, because there's Google Colab. Kaggle itself actually lets you run kernels in there. So probably we'll add some information on that. Google Colab, and then you can also use Google Cloud. One team from the first section actually got the $300 of free processing time on Cloud and use that. There's another thing. We use this at RGA. They're called spot instances. So checkpointing is very important. You get those GPU instances on Amazon Cloud for like 10% of what they would normally cost. There's no way you would get them during the COVID-19 outbreak, but the thing is, you get them for 10% of the normal cost or around that area, but they can take them away. So as soon as they have a paying customer, the Amazon Cloud takes it away. So you write the code to checkpoint it and store that result off to S3 or something like that. So the checkpoint, very good use of checkpointing. I know when I looked at your code, I liked that you were using that. I did not cover checkpointing in this class. That is definitely something that I'm adding in for the next semester on this. You gave a very good overview of Google Colab. That was good. The ensembling, to talk some about that, I liked your approach using linear. Now, when you say linear, did you fit a linear regression to it to figure out the coefficients or the weighting, or how did you do that exactly?
Here, as you can see in this slide, and I predicted the outputs of these two models.
Okay.
And I have
average them.
Just simply average them. And it leads to the 0.68 RMSE.
So I mean, you definitely had the same perception of ensembling. Like the first time I used it, there was a Kaggle, and definitely getting into there's a real Kaggle that I competed in once that I was like number 2 on the leaderboard and got pushed out of that quite rapidly. So I mean, believe me, that happens in these. The first Kaggle I ever got into the top 10%, I used ensembling for the first time. I think this was like 3 years ago, and it was just like magic, because it's like, how do these two weaker models ensembled together do so well? And that seems to be your perception.
Exactly.
Well. And then the next thing that I did was, I was so short of time on that Kaggle, which believe me, that's just how you feel in every Kaggle. I manually adjusted the weightings. So I went with a 40-60, and I went with two 40-60s, just both in each direction of my top 2 models, submitted it to Kaggle, and saw what Kaggle did on the public leaderboard. And I saw that one was considerably better than the other. And I just adjusted that percent completely manually, the weighting, and upped my leaderboard position. So that's a real quick approach you can do that downside is you are definitely overfitting the leaderboard a little bit when you do it that way, but not so bad. And then you can also, if you look on my GitHub repositories, I have some examples of ensembling where you actually fit a linear regression to it, and then you get coefficients. So I could throw 20 models into it the way that I have, and it'll give you a coefficient for each one. And the ones that have low coefficients are just not your strong models. And then that way, machine learning tells you what the optimal weightings are. So just a few ideas there.
Thank you.
But yeah, very, very good presentation. Very good. I looked at your code. Very, I liked your use of ensembling, and very good use of checkpointing. Definitely a way to get in those hard cutoffs where you were that Google Collab's going to impose on you. Oh, one question from the class I see somebody typed in. So you iterated each pixel.
Do you mean the pre-processing step?
I think that's what they mean.
Okay. Yes, actually, yes. I use the apply along axis, and the axis is gonna be I pass the index of 2, which means every pixels is passed into this function.
What was the runtime like on that? Did that take a while?
Actually, yeah, it's gonna take a while.
Okay.
Yeah, I can't remember how long it take, but it's gonna take a while.
And I assume you probably saved the binary or pickle or something of that process, so you didn't have to repeat it a lot.
Yeah.
Okay. Any other questions? Okay. Well, thank you very much. Very good presentation. Very good code. Thank you for watching this video. And if you're interested in this kind of thing, following my class, please subscribe to my YouTube channel. And thank you to the students for presenting and doing all the hard work on the Kaggle competition.